This video is going to show you some of the math behind constructing perpendiculars and means so that you'll have some idea of why the constructions work. Now, a lot of these constructions rely on properties of a rhombus. A rhombus has four congruent sides, and its opposite sides are parallel to each other. The diagonals of a rhombus are always perpendicular. The diagonals go from one corner to the opposite corner. And the diagonals will always bisect each other, which means they'll cut each other into two congruent pieces. So when we make these constructions, quite often there's an implied or unseen rhombus within the construction. So our first construction was to construct the perpendicular bisector of a line segment. And our construction looked like this. Now the rhombus is something we didn't draw, but it's implied in the picture. Because when we constructed these arcs, we didn't change the size of the compass, which means the length from the end point of the line segment to where the arcs intersected was always the same. So there's the implied rhombus, and you can see that the diagonals of that rhombus are the line segment we started with and the line segment that we drew through the intersections of the arcs. So we have the diagonals of the rhombus intersecting each other at right angles, and we have the diagonals of the rhombus bisecting each other, so they bisect the line segment AB in this case. Our next construction was to construct perpendiculars to a line through either a point on the line or a point not on the line. This was the construction of a perpendicular to a line through a point on the line. And our first step in the construction was to put the point of the compass on point P and then draw the two arcs on the line. And then from those two arcs, we drew arcs that had the point of the compass at the intersection of the arc and the line, and then we had arcs above the line. And we did not change the size of the compass to draw those two arcs. So in essence what we did was we drew two arcs that indicated the lengths of two congruent line segments. Now we could also have drawn arcs below the line segment, but we didn't really need to. If we had, they would have intersected right about there, and we could see the four congruent sides of our rhombus. If we're constructing a perpendicular to the line, then the perpendicular is really going to be one of the diagonals of the rhombus that's implied in the construction. This was the other construction. Construct a perpendicular to a line through a point not on the line. And in this case, we started by putting the point of the compass on point P, and then we drew these two arcs, which are going to be one of the diagonals of a rhombus. Now, since we didn't change the size of the compass from these two arcs to these two arcs, we really constructed a rhombus. And you can see that what we have is two line segments now that really are the diagonals of the rhombus, and we know that the diagonals of a rhombus are perpendicular to each other. When we construct the arithmetic mean of two line segments, we're also going to see an implied rhombus in the construction. You remember that when we find the arithmetic mean of two numbers, we simply add the two numbers together and divide by 2. Let's see if we can find that in the picture. So if we call the length of one of our line segments x, and then the length of the other line segment y, you'll remember to start the construction, we copy those two line segments onto a line. And then we construct a perpendicular bisector of that line segment that has an entire length of x plus y, which means we're really constructing this implied rhombus. And since the diagonals of a rhombus bisect each other, then that distance from the center of that rhombus to one of the endpoints, which in this case is called F, is the arithmetic mean. It's that entire distance from E to F divided by 2 because the diagonals of the rhombus bisect each other. When we constructed the geometric mean of two line segments, we had some rhombuses that were implied in the picture because we were doing some bisecting of line segments. But what you'll see is that in order to see how the mathematics of the arithmetic mean fit into the geometry of the picture, we're going to have to use some algebra to get there. So you remember that if we have two numbers, x and y, if we want to find the geometric mean of those two numbers, we multiply the two numbers together and then take the square root of that product. When we construct a geometric mean of two line segments that have a length of x and a length of y, the first thing we do is try to copy those two line segments onto a line so that we have the sum of the two line segments, and then we construct the perpendicular bisector to that combined line segment that has a length of x plus y. Now that's the implied rhombus in that construction, and we've seen that already. The rhombus that will give us diagonals that are perpendicular to each other and that bisect each other. Now we also know that the distance from the center of that rhombus to one of those endpoints is the arithmetic mean. So that distance would be x plus y over 2. Now let's take the rhombus away and take a look at these line segments. That point where the two line segments that we initially drew, the x plus the y, that point was an important point in the next step of the construction, because after we constructed the semicircle that had an endpoint at what is labeled point C in this picture, then we had to construct a perpendicular to our original line through that point. And the length of that line segment from the point up to the semicircle was our geometric mean. So now let's see if we can figure out how we could write that geometric mean, the length of that geometric mean, in terms of the length of our two line segments, which are x and y. So the first thing we're going to have to do is look for the length of that little red line segment. Now, this is a little bit tricky to see. What you have to keep in mind is that that little red line segment is the length from point C to the end point of that yellow line segment, which has a length of x. So how can we figure out that length? Well, this line segment has a length of x, and this blue line segment has a length of x plus y over 2. So that means what's left, that little red line segment, has to be the difference of those two measurements. So the length of that little red line segment is x, the length of the yellow line segment, minus x plus y over 2, the length of the blue line segment. Now you might be wondering, why is that important? Why do we need to know that distance to figure out how long this geometric mean is? And it has to do with the Pythagorean theorem. So the blue line segment is really a radius of this semicircle. So we could take that blue line segment and redraw it up here, and it would still be a radius of the semicircle, which means it would still have a length of x plus y over 2. And now you can see what we've got is a right triangle. And if we have a right triangle and we know the lengths of two sides, we can always use the Pythagorean theorem to find the length of the third side. So we'll call the length of the third side, which is our geometric mean, we'll call it G for geometric mean. And then we'll use the Pythagorean theorem to solve for G in terms of x and y. Now this gets a little bit complicated, but I'm going to show you what it looks like and show you all the steps. You can take your time later on to kind of work your way through the algebra. But if we very carefully simplify each side of the equation and try to solve for G, we'll get down to G squared equals x times y, which means G is plus or minus the square root of xy, which we know is the geometric mean of two line segments. So this one's a little complicated algebraically to get to the length of that line segment G, which is our geometric mean, but we can actually make some sense of connecting the geometry to the geometric mean through a little bit of algebra. Now we'll need a little bit of algebra to understand how the harmonic mean fits into this construction as well. It's not quite as complicated as the geometric mean though. So in this construction, you'll remember that we have these two line segments. They each have a different length. We take those two line segments and the first thing we do is we construct a perpendicular bisector to the sum of the two lengths because we need the arithmetic mean of those two line segments. So that blue line segment is our arithmetic mean. And then the next thing we do is construct a perpendicular to a line through a point. So in this case, we've done the construction right here. Then we copy some of those lengths. So the length of the orange line segment we've copied right there, and the length of the yellow line segment we've copied right there. And then we copy the length of that arithmetic mean in this position. The red line segment is our harmonic mean. So let's label some things. The x is the length of the yellow line segment, the y is the length of the orange line segment. And if we have two numbers, x and y, and we want to know the harmonic mean, we know that we can take 2 times x times y over x plus y. So let's see where that is in the picture. This is our x, and since we've constructed a rectangle in our construction, we can actually move that line segment over to the opposite side of the rectangle. And our y, we can do the same thing. We can move it to the opposite side of the rectangle. Its length will still be y. And we've also got two triangles that are being formed in our picture that are important because they are similar triangles. They have the same angle measures even though they are different sizes. And one of the properties of similar triangles is that their corresponding sides are proportional. So corresponding sides means kind of matching sides in the two triangles. So in this case, the blue line segment, which remember was our arithmetic mean, corresponds to a length we called y. And the yellow line segment, which we're going to call a length of x, corresponds to the red line segment, which is our harmonic mean, and we'll call that h. So since we have two similar triangles, the lengths of corresponding sides are proportional, which means if we, in a ratio, compare x plus y over 2 to its corresponding side, which is y, that will be equivalent to the length of x over the length of h. So now remember, h is the harmonic mean, so we're trying to solve for h. And to do that, we can simply cross multiply. Multiply both sides of that equation by the reciprocal of x plus y over 2, and then do a little simplifying. And we do have h equals 2xy over x plus y, which is exactly what we said the harmonic mean should be. So you can see some of the math behind the constructions gets a little complex. Some of it is fairly simple because it's just based on properties of a rhombus.